All right, so this presentation is going to focus on identifying and determining types of intermolecular forces. So we're going to talk about two main groups of intermolecular forces. One has kind of like a subcategory underneath it. And then there's also a fourth one, which is kind of like what I like to call the in-betweener. Like it kind of makes the connection between an intermolecular force and an intramolecular force. So remember, intermolecular forces are the forces that occur between molecules, between covalent molecules, and intramolecular forces are really referring to bonds, covalent bonds and ionic bonds. The diagram down at the bottom here shows you that there is a lot of overlap between types of bonds and their strength. So there are some covalent bonds that are stronger than some ionic bonds that are stronger than covalent bonds. So there's kind of a lot of overlap there, but in general, intramolecular forces are stronger than intermolecular forces. And we're going to talk about those four intermolecular forces you see down there. But again, I consider one of them to be kind of like your in-betweener. We'll talk about that one. One is kind of like a subgroup. We'll talk about that one. And then there's two kind of like main ones. Okay, so let me list the four intermolecular forces. So the one is called London dispersion forces, not because it was discovered in London, but was discovered by a guy and his last name was London. The next one is called dipole-dipole forces, and dipole-dipole forces occur only with polar molecules, which is why it's really important that you understand the idea of molecular polarity from last week. And within dipole-dipole, there's a special type of dipole-dipole force, and it's called hydrogen bonds. It is not a true bond. Despite the fact that it's called hydrogen bonds, it is not a true bond because it's an intermolecular force. And in chemistry, true bonds are called intramolecular forces. So I don't know why they named it that. I wish they would have called it hydrogen attractions or something like that, but they didn't. They called it hydrogen bonds, but please remember it's not an actual bond. And then we've got our ion dipole forces, which I consider to be kind of like your in-betweeners, okay? The diagram at the bottom kind of shows you their relative strengths. So dispersion is generally the weakest, dipole is generally in the middle, and hydrogen bonding is generally a little bit stronger with a crossover of ion dipole, okay? And again, I say generally because there is a little bit of overlap here, right? So like there's some dispersion forces that are just as strong as some dipole forces. There's some hydrogen bonding forces and some ion dipole forces that are equally as strong. So there's a lot of overlap. So just like when we talked about chemical bonding, it's not as cut and dry as we would like it to be. The same thing is true about intermolecular forces and their strengths, okay? All right, so the first one we're going to talk about, and the one that I believe is actually the most complex, are called London dispersion forces, all right? First of all, London dispersion forces are the weakest forces because they tend to result only from temporary changes within atoms. And we'll talk about what that temporary change is, but it has to do with electron movement. And because it's only a temporary split-second change, it makes these the weakest forces. London dispersion forces exist between every single covalent molecule, regardless of the type and regardless of what else is going on. You always have at least London dispersion forces. There are lots of molecules that have more than one intermolecular force because every single thing has London dispersion forces. Other molecules may have things in addition to London dispersion forces, but every covalent molecule that is attracted to another covalent molecule has London dispersion forces holding it together. And for that reason, it's typically the only intermolecular force of nonpolar compounds. And again, this has to do with just the fact that there are electrons and electrons are constantly moving. I will try to explain it in the next slide. And then the next Nearpod slide is going to go through a video that kind of shows you an animation of what it actually looks like. Okay. So why do London dispersion forces occur in the first place? So let's take a very simple example of two helium atoms like are shown here, okay? So we have two helium atoms shown in the top here, and this is showing our subatomic particles. So electrons we know are constantly moving around each atom, all right? So if I put these two atoms close enough together, occasionally the electrons would line up, both electrons may be on the left side of this atom B because they're randomly moving and occasionally they'll end up like that. So what happens when both of those electrons end up on the same side of atom B because they're randomly moving and they just so happen to be there? Well, what happens is that these electrons end up over here, and for this split second in time, that helium atom has a partial negative side where the electrons are located, making the other side partially positive because we've got all of our negatives over here of the helium. So we're talking about helium, which only has 2 electrons. You can imagine if there's a molecule that has, say, hundreds of electrons, there is the chance that all hundreds of the electrons end up on the same side of the molecule at the same time. It doesn't happen very often, but maybe 80 of them end up on one side and only 20 on the other side. So you can see how this is very temporary, right? It's just because electrons are constantly moving that they might just so happen to end up on the same side of the molecule or the same side of the atom at the same time. So we end up with an area of our molecule that's temporarily partially negative and temporarily partially positive. And that's what this image is showing here. For this split second, this is temporarily partially negative because all the electrons happen to be lined up on that side. And this side of the atom, or even a molecule, this could be multiple atoms, this side of the atom or molecule is partially positive. Well, if this is negative over here and positive over there, the negatives on atom A, the electrons on atom A are like, whoa, we don't like other electrons. So they kind of get pushed away to the other side of atom A. So the electrons of atom B are lined up here, and they're also going to stay there for a little bit because they're going to be attracted to the protons of atom A. Well, in the meantime, as they're attracted to the protons of atom A, they're repelling the electrons of atom A. And so the electrons of atom A move to the opposite side of atom A. So what you end up with are two atoms that you see at the bottom that are partially positive and partially negative. And because they have partially positive and partially negative sides, they can attract each other because positives and negatives attract. And again, remember, this is very temporary because this is only going to be true while those electrons are in those positions. Those electrons aren't going to stay there. They'd have no reason to stay there. They're going to continuously move. But for the split second that they're right there in that exact location, there's going to be that attraction there. And when I say the split second, we're talking about nanoseconds and even smaller than nanoseconds because remember, electrons are moving super duper fast. So London dispersion forces, while we say they are temporary forces, please remember that within 1 second of actual time, there could be 100 times that these electrons end up in the right spot, creating that London dispersion attraction between two atoms or between two molecules. However, there are a lot of times where those electrons are not lined up in the right place to create partially positive and partially negative sides. And as a result, we say that these London dispersion forces are relatively weak because they only happen by chance and randomly, and they're not permanently there. There's no reason for the electrons to stay on those sides of the atoms. They have no significant attraction. It's just a small, slight attraction for a split second in time, okay? Now, why are London dispersion forces really important? Okay, so let's take a look at this. So remember when I talked about inter versus intramolecular forces, and I talked about the importance of intermolecular forces in determining the properties of covalent substances. So one of the properties that we look at with covalent substances are their state of matter at room temperature, okay? So for example, we can look at the halogens. Fluorine is the halogen at the top of the periodic table with only 9 electrons in each fluorine atom, but fluorine is diatomic, so it always exists as 2. So a fluorine molecule contains 18 electrons. Chlorine is right below it, and I believe that chlorine has 17 electrons each, and chlorine is also diatomic, so that would be a total of 34 electrons in chlorine, okay? And then we would continue going down our periodic table. And what you should notice is that the top of the periodic table, you're more likely to find these things as gases. That tells me that their intermolecular attraction is not very strong. The reason they are gases is because they're able to move independently of each other. They're not really attracted to each other, so they just kind of randomly move. Maybe occasionally they get close enough to get some attraction, but for the most part, they're just randomly moving around independent of each other. Then we get down to bromine. Bromine has way more electrons, and bromine's also diatomic. So now we're talking like, okay, so we've got more electrons. So now there's a greater attraction. When all of those electrons on a bromine molecule move to one side, it's more likely to attract another bromine molecule. Okay, so stronger London dispersion forces because we have more electrons that can cause a greater attraction, but still not super strong. So strong enough to maybe make it a liquid, but not as strong to make it a solid. Then we get to iodine. At room temperature, iodine is a solid. It is not a brittle solid like we would see in an ionic substance, but it is still a solid. It's just kind of like a soft, powdery solid. The only reason it's a solid is because iodine, each iodine atom has so many electrons that once all those electrons in that diatomic molecule, once all those electrons can move to the same side and they go next to another diatomic iodine, that causes a relatively strong London dispersion attraction between the iodine molecules. That relatively strong London dispersion attraction exists to create enough to create a solid at room temperature. And again, it's not going to be a super hard solid because intermolecular forces are weaker than intra. And so when we talk about solid ionic substances and we talk about them being very hard, those ones are really, really hard because the solidness is due to the fact that the ionic bonds between them are super strong. In this case, when we're talking about iodine, like there is a strength of attraction between the molecules, but it's not nearly as strong as what was between the ionic particles, okay, the ionic ions, all right? So one thing to notice about this is that the larger the particle size or mass, the stronger the London dispersion force. And the stronger the London dispersion force, the more like a solid you are, all right? And the reason being, it's not because there's more mass, it's actually because more mass means more electrons. And more electrons means you can have a greater charge difference when you have those temporary dipoles. And if you remember back when we talked about Coulombic attraction for lattice energy, charge is one of the factors, it's the most important factor in determining a strength of attraction. We talked about charge in determining the strength of attraction of lattice, but in this case, we can talk about temporary charges moving to one side of the molecule to cause an attraction between two molecules. And it still holds true that the bigger the charge, so the more electrons that are able to move, the bigger the attraction, okay? We call this a greater polarizability, a greater ability to become more polar. And polar, again, refers to the fact that we would have positive poles and negative poles, okay? The second thing that we want to make sure we take into account about London dispersion forces is that the larger the area where the electrons can kind of be drawn to, the stronger the attraction is going to be. So on this diagram, you see these are all versions of pentane. These are called what we call isomers. So it's basically the same chemical formula, so it has the same chemical makeup, but they're arranged a little bit differently. This is different than resonance. We talked about resonance with Lewis dot structures. Resonance with Lewis dot structures was arranging bond differently, like a double bond was moved from the left to the right. This is actually rearranging the physical atoms and the way that they're connected in the molecule, okay? So you can see that N-pentane, letter A over here, has more surface area. So that means there's more locations where the electrons can be kind of drawn out to attract to other molecules. You can see on the right side here, neopentane. Neopentane has less surface area. So there's less areas where the electrons can kind of like congregate on the outside. So there's going to be less attraction, okay? So two things help control the strength of London dispersion forces. One, and the biggest one, is how many electrons are there? The more electrons you have, usually determined by more mass, the more electrons or more mass you have, the stronger charge that can be mobile that can cause London dispersion forces. The second thing is the bigger the molecule, meaning like the more surface area it takes up, the stronger the London dispersion force because there's more spaces where electrons can congregate to create that partially negative side and partially positive side. Stop this video here and there will be another one for the further ones.